Hello, this is PETTaLS version 1.7 tutorial video number 9. And in this video, I'm going to be talking about the one position sound pressure level response window down here in the lower left section of the results tabs in the PETTaLS window. So PETTaLS is an application that I wrote that lets you simulate and design loudspeakers using exciters that are attached to all sorts of surfaces, like your desk or a window or a piece of plastic or whatever you want. And this is video 9, so hopefully this isn't the first video that you're watching. And if you're interested in this, please go back and watch the other videos first, where I've talked a lot about this particular window and these particular results before, which right now are showing the on axis at 1 meter away sound pressure level response in decibels of the default setup that comes up when you load the program, which is an acrylic panel. So that's plexiglass 3 millimeters thick, clamped at all 4 edges, 23 centimeters wide, 35 centimeters high, with an infinitely large enclosure, so no enclosure essentially, and a single small exciter right in the middle of the panel. And the surface looks like this. Here is the dimensions of the panel. Here's where the exciter is, right in the middle. This is the vibrational pattern at 20 kilohertz, the highest simulated frequency. And so the sound pressure level response that we get looks like this when you're a meter away from the speaker looking directly at it in an anechoic environment. That's important to keep in mind. And with the speaker totally baffled so that you don't get any rear cancellation effects. So there's also on this window two things that I'm calculating, which are the mean sound pressure level and the standard deviation of sound pressure level. And that's being calculated over all simulated data points. So that, like, see, starting from 20 hertz, we have less than 20 dB of sound pressure being created. And so those are really dragging down the numbers here. The usable frequency range of this loudspeaker is probably about 100 hertz to maybe the coincidence frequency, which is, what is this, like 12 kilohertz? Let's just say 10 kilohertz to make it simple. So 100 hertz to 10 kilohertz is what I'm going to call the interesting frequency range of this loudspeaker. So that's where I'm going to evaluate these metrics. So if I go back to this screen and change the frequency range to 100 hertz to 10 kilohertz, and I talked about this window in a previous video. Oops, and rerun the simulation. The number of modes being simulated goes down, so the simulation should run more quickly now than it did before. The simulation time is pretty much directly proportional to the number of modes in the speaker, and the mode cap is set at 1500 modes just to keep the program from crashing people's computers. I have tried to run simulations up to about 9,000 modes, and that's where my computer ran out of RAM. So I just capped it at 1500. So okay, now we're only simulating this orange line, and I overlaid the new results on the previous results just to show you that they match up. So the orange line is the same simulation from 100 to 10 kilohertz, and the mean SPL went up and the standard deviation of SPL went down. So mean is 72.46 dB, standard deviation 6.65 dB. I'm actually going to do average horizon level because when you add in a bunch of room reflections and things, this is probably a bit more of what you're going to see. We're not in an anechoic environment, so these off-axis radiation patterns are going to probably be reflected everywhere. So this is, you know, I just like this better. Okay, so because there's not a whole lot more to talk about, and to make this video interesting, I'm going to run an experiment, which is I'm going to use the same speaker, but let's say I'm designing now like a fun product for myself or for a company. And I'm going to keep the same acrylic panel with the same dimensions, but I'm going to now mount this on the wall. So I'm going to mount it maybe 5 centimeters from the wall. So the box depth is 5 centimeters. Same exciter. I'm just going to use this exciter, which is, it's a low power exciter, but that's fine. It's cheap. If you're making a product with a company, that's cheap is good. Because it's going to be in a box that's mounted to the wall, I'm going to keep this baffled box checked, which means that the rear reflection will not cancel out the front reflection. And we're going to do average horizon level still. So let me get rid of those results. I'm not going to compare this to the new set of results. But what I'm going to do now is find, in terms of these two metrics, what's the best location to be placing the exciter? And there's a million billion ways that you can define what the best location is. There's no right answer to this problem. But I'm going to say the best location will be based on having the highest mean SPL and the lowest standard deviation of SPL with the average horizon level response at 1 meter. So let's start with the exciter pretty far in the corner and run this simulation. So now, if I put this on briefly, the exciter's down here in the corner. Now I don't have to run the exciter every single place on this panel because there's 4 quadrants of the panel that are going to be totally identical in terms of a single exciter placement, as long as I'm looking right at the center of the panel when I'm listening to it. So I only have to test locations in a single quadrant of the panel. Okay, so the simulation is getting mad at me because of the screen capture software. So we just got to get to 10 kilohertz. And then we'll get some results here. There we go. Wow, that's a terrible response. Yep. Don't really want to put it in the corner. So, okay, the mean SPL was 46.7 dB, and the standard deviation of SPL was 14.52 dB. Now, that standard deviation doesn't actually really come from the big peaks and nulls. It comes from the fact that it slopes up. So I've created an Excel spreadsheet, and I'm going to type in those numbers. 46.7, 14.5. Cool. Now let's run the next one. And as you can tell, this is going to take a while, but that's research. So I'm going to speed up this part of the video because I'm just going to be running a ton of simulations. Each individual simulation doesn't take very long, so hopefully this will be over quickly, and then we can analyze the results. See you then. Okay, I'm back. It's a different day. Not like the simulations actually took multiple days, but I just had to wait to make the rest of this video. So I defined a couple of metrics to help me pick out the best exciter location. Up here, I did the mean divided by the median. So I want high mean SPL and low standard deviation of SPL. And the highest number comes out being this point, which is F6 here. So that's 0.25, 0.25. I also defined another metric, which is the mean minus the standard deviation. And there are 3 maximum points there, which are 66. That's here, here, and here. So that is what? F11, that's 0.25, 0.5, G6, which is 0.3, 0.25, and H6, which is 0.35, 0.25. I kind of like this metric better. There's no right answer to these things, but after playing around with this for a little bit, I like this metric better. So 0.25, 0.25 came out to be the best exciter location based on this metric. That doesn't mean it's the best exciter location ever for all panels. It's just for my metric and for this specific setup, that's what has the highest value. So looking back at the simulation, here is the full frequency spectrum for that single point. So this is average horizon level response again. So we see actually not a terrible response. There are no, there's peaks and dips down here at low frequencies up to about 1K. It's not as bad as other points that you can put the exciter. And then above that, average-wise, it's pretty flat. If we just look at a single point, it isn't as flat. But in the average, it is flat. And if you start including room reflections and things, you're probably more likely to see something closer to this average. So there you go. There's one way that you can use this type of graph and these metrics to hopefully define for yourself and your project what exciter location is going to be best. So thanks for watching, and there are going to be more videos made soon. So I'll see you there.